Okay, YouTube, this is my first video on a module that I'm doing on sketching transformations of exponential functions. And essentially what we'd like to be able to do in this video and subsequent videos is, since we've already been looking at graphs of exponential functions, and I'm going to say the most basic form of an exponential function would be this y equals some base to the power of x form, where this base, we know that the base is both positive and the base is not equal to 1. But for something that's like this here, essentially we've seen some pretty basic patterns with them. That is to say that we know that all of their graphs, at least this parent function here, they have an asymptote on the x-axis, okay, let's say y equals 0. And if b is greater than 1, okay, then we have growth. If b is less than 1, we have decay. But I'm going to say more generally, I'm just going to draw a growth curve here just to say that we see some patterns here. But for a growth curve, we would have some graph that looks like this. And in terms of key points here, we've seen that this point 0, 1 is always on this graph of b to the x, because anytime we plug in 0 and take some base to the power of 0, we always get 1 for an output here. So we say 0, 1, and then just more generally speaking, I would say that if you plugged in 1, anytime you plug in 1, okay, for this parent function right here, we would say plug in 0, we get 1. But when you plug in 1, we would get b to the power of 1, which essentially presents us with the base. And so we're going to put this general point on here. We're going to say that every exponential function, at least growth that looks like this, and decay would look, you know, kind of the other thing but flipped around the y-axis, but looks like this, where we have an asymptote at y equals 0. We have an intercept at 0, 1, okay, y-intercept, and then we have the point 1, b that is also on our graph. So with these three distinguishing points, what we want to be able to do is transform this graph, okay, b to the x, into any other graph that maybe we could shift it left and right, or perform what we call a translation, or we could stretch this graph vertically or horizontally, or we could reflect it over the x or y axis. And so what we're going to do essentially is we're going to look at the different transformations of this parent function here, and to do this we're going to use the parent function, okay, y equals 4 to the x power. And so let's go ahead and be clear on something here. I'm going to try to scroll up as far as I can here. Up in this little corner here, we're going to give this a name. We're going to refer to this as the parent function. And in order to transform, or at least sketch all of our transformations, what we're always going to do is sketch the parent function first and then modify it using these transformations that we see here. And so in this particular case, we're going to say that our parent function, okay, parent function is y equals 4 to the x power, and so our base is 4. And so what I'm going to do is I'm going to pop this over in the Desmos here. We're going to just kind of do this here. We say y equals, and I'm going to do b to the x, but what we'll do is we'll add in a slider here and make our base equal to 4. And so what we see here is this. Suppose I want it to be red. Personal preference here, and we'll put this in projector mode. We can see some things here. We have an asymptote on the x-axis. We go through 0, 1, and we notice that in this particular sense, in this case, we go through 1, whatever the base is here. And so for this exponential curve, what we're going to be doing is modifying it by saying that every other function we draw, there could be any other function that's not the parent function here, we're always going to use f of x to mean the parent function, which in our case is just some b to the x power here. What we're going to be doing is saying that that f of x right there, we could write any other function g of x really as some transformation of f of x. And so what we're going to say is that all transformations of our exponential functions g of x will be some modification of f of x. And so we usually express this as a times the function f of x minus h plus k. And so we're going to run some commentary on this here, but what we're also going to do is we're going to rewrite this one final time and say that the way this really manifests itself in an exponential function b to the x is really this. We get something that looks like a times b to the x minus h plus k. And so what we're going to see here are some things. We're going to see that h and k are responsible for horizontal shift, okay? This is also known as a translation, or in vertical shift, respectively. And so what we see over here is this. Horizontal translation, we write this in function notation, is that g of x, our transformation, is our original f of x, but minus some h here. But when you look at the function, really we start to see things like this. We say 4 to the x minus 3, and you got to look at it this way. X is in parentheses with the 3, and x is in parentheses with this 2, and so we can easily identify h because it's always paired with our x. And one thing to mention about h is h is backwards. So without going into too much detail here, what I will point out is that in the formula here, because h has a subtraction relationship in front of it here, a minus sign, then whatever we put in for h is going to look to be backwards here. And so in this case, we could say that in this function here, h is equal to 3, and h here is equal to -2 in this. And so we could see that h is going to be responsible for our horizontal shift here, whereas k, where I mentioned our vertical shift, okay, is our vertical translation. We say that the k value, notice, is not in parentheses with the x, but on the outside of our function. So we say that our transformation g of x really is the original function f of x, where we've just added on some constant to all of the original y values, or subtracted off. And so what we see here is it would look something like this. Using our parent function 4 to the x, we get 4 to the x plus 5 and 4 to the x minus 1, where this plus 5 and minus 1 are not associated with our x values here. And so we can see that, plus 5 would actually shift us up 5, and minus 1 would shift us down 1, whereas up here we said minus 3 shifts us 3 to the right, and plus 2 shifts us 2 to the left, where h is backwards. And so we say k is honest. And so what I want to do is I just want to kind of go play around with our graph here. And what we're going to do is up here in the formula, suppose I'm going to throw some parentheses around our x here. We're going to say minus h. We could add a slider for that. And then down here we'll say plus k. And so I'll add a slider for all of these, but I'm going to set h and k back to 0 and 0 just to show you that when h and k are both 0 and 0, really what we would have is y equals b to the x in the first place. So this is the same as our original graph, but look what happens when we start making h5. Look what happens to our graph. That point that was at 0, 1, okay, now is 5 to the right, and so now is at 5, 1. In other words, we shifted everything on our graph 5 to the right. Whereas if I were to make h, say, a -2, everything on our graph, 0, 1 would become -2, 1, because everything on the graph shifted to the left too, including the asymptote, which would be insubstantial here. We could always say that the asymptote is going to be at the height y equals k. And so I'll put in a dotted line for this right here. We can modify it. So there's our asymptote. But you can see that h shifts our graph left and right, whereas k is going to be shifting our graph up and down. Now you'll notice that when I shift k, say, to be a 3 here, for instance, we look at our transformations. Look at our transformations here. We say, k, if we put a plus 5, it shifts our graph up 5. Minus 1, it shifts our graph down 1. This, to be clear, shifts also our asymptote. And so, for instance, if we were to say k is plus 3 here, well, then our original graph, which went through 0, 1, would now go up 3, would go through 0, 4. And also to say what else this does, I suppose that instead of going through 1, 4, okay, that point goes up another 1, 2, 3 here, and it would go through 1, 7. You'll look at the asymptote here. We'll notice that the asymptote's at y equals k. Well, we say in this case k is 3, so y equals 3 is going to be our asymptote. So something like this would have a domain of all real numbers and a range of y is greater than 3. All y values greater than 3. So we can see that h and k are responsible for translations. Now let's talk about reflections. Okay, so reflections, the interesting thing here is this. Sorry to cross through my text here, but I'm going to do that. We can see that when you plug in a negative x, okay, or put a negative in front of the x, this is going to be a reflection over the y-axis. So we say negative x means over the y-axis. Okay. Whereas when we look at this, and it'll fill in here in a second, there we go, we see a negative y, okay, a negative in front of our f of x is really the same thing as a negative in front of our y. And so when you make your y value negative, we'd say our transformation would look like this. This really is a negative out in front of our function. So you can really tell when the negative is in front of the x because it's up here with the x. When it's out in front here, we'd say that this is really a negative y, and so we say negative y implies over the x-axis. And so it's kind of this backwards relationship. So I just want to show you here, as we go over to Desmos, let me put h and k back to 0 and 0 for the time being. But if we were to wander up here and just say, hey, throw a negative in front of our x value here, you could see that everything flips over the y-axis. And just to show you again here, I'll backspace out. Here's our normal function. Negative in front of the x flips over the y. Now you'll notice that if I were to make a negative go out in front of our y value, which really shows up in front of the b here, everything flips over the x-axis. And so we would just make our normal graph, but flip it over the x-axis there. So we'd say negative in front of our y flips it over the x, negative in front of our x flips it over the y. And so for our final transformation here, we'd see that we have shifts, reflections, but we also have stretching and shrinking. And so the important stretches and shrinks we'll see we indicate with some a value. And you'll notice that I really wrote my a value out in front of our parent function here. This is the one you really want to know, this form right here. Basically, we could say that, let's point this out here, we say a in front here, when you notice this, it's in front, is vertical stretch. And so we say a is vertical stretch. Okay, so A being vertical stretch there, why do we use also an A in here to indicate horizontal stretch or shrink as well? And so we can see that we use an A in here to be consistent with what we're doing, but when we take our X values times an A value, it actually stretches it horizontally, and when you take your Y values, okay, times an A value here, you stretch it vertically. And so that's how that works. We're really going to see this A represented out front more often than in front of the X. But sometimes you do see it in front of the X, and so what we'll do is we'll add in a parenthesis here. We're going to say this is some letter C, and C is our horizontal stretch and shrink. And maybe you have more room on your paper to fit this in, but stretch and shrink, whereas this is our vertical stretch, and I suppose we should write shrink as well. Okay. So what we're going to see here is this. If we have A being out in front, okay, then we would say that A times our original function would stretch everything by a factor of 3. Or if I had a fourth out in front, say, it'd shrink it by a factor of a fourth, or stretch it by a factor of a fourth, which is really shrink. So you can see if the A value is out in front, which is typical, it's what we often see, then it's just going to stretch or shrink by a factor of whatever that is. Now, if you have a C value or a coefficient of X, and I would say that, I want to rewrite this here, this is 4 to the 1/2 X right here is the same as X over 2. We can see that when X, its coefficient is 2, it actually shrinks by a factor of its reciprocal, okay, reciprocal factor of C value, okay, which is this coefficient of X right here. But basically, if this were a 1/2, then it would actually stretch by a factor of its reciprocal, which is by 2. And so just to show you on our graph here, what we're going to look at is, if we were to go now add in an A value, usually, okay, add in a slider here, we'd say A is 1, okay, our graph would go through 0, 1, but you'll notice that when I make this, say, 3 here, our entire graph stretches by a factor of 3 vertically. It stretches away from the x-axis. And so if I make this 3, we've seen this before where that A value is just our initial value. And so we say it starts at 3 and then, goes up whatever, goes down whatever, depending on growth or decay. But we'd say all of our Y values now have just tripled because we took them all times 3. Or all of our Y values could be halved if we take them times a half. And so we'd see vertical stretch and shrink caused by A out in front. If we put in a C value here, you can see horizontal stretch and shrink occurring with our graph by a factor of its reciprocal. And so in our following video here, what we're going to be doing is saying, now that we've kind of looked at these transformations, what could we say about the graph of, say, this function here, 1/2 to the x compared to 1/2 to the x minus 4? So I'll meet you in the next video. Cheers.